Welcome all of you. Today we'll be discussing the fourth module of the subject PSA, that is Automatic Generation Control. In the syllabus, this is a very small syllabus which mainly addresses load frequency control and voltage frequency control, its modeling. Okay, so again, this is purely theory oriented module, of which the modeling part and some concepts can be asked in the exam, both in short answer as well as in essay part. Now let's proceed with this module, automatic generation control. Now the reference text that we are using here is Modern Power System Analysis by D.P. Kothari. See the syllabus. Syllabus is only this much, that is the load frequency control, single area, two area, and the automatic voltage control. So we'll be discussing the basic concepts as well as the modeling part of single area, two area, and voltage control. So essay can be asked from any of these sections, so please do not skip any portions coming under this module. Now let's proceed. What is the need for AGC or automatic generation control? Okay, so as we already know, power generation will be having both active power component P and reactive power component Q. So automatic generation control means we are going to control the active power P or the reactive power Q automatically. So why do we need an automatic generation control? So the reason is that the active power P as well as the reactive power Q, they are not constant. They will be continuously varying. And how do they vary? They vary depending upon the load requirements. Okay, so if the load, depending on whether the load is active, whether the load is reactive, depending upon those requirements, the demand for active power P as well as reactive power Q varies. So it is always required to continuously monitor this active power P and reactive power Q. Okay, so for that we need some control aspect which will control the active power P and reactive power Q automatically. That is automatic generation control. Now we will see in detail what is automatic generation control later. Now let's see what will happen when active power P and reactive power Q varies. Why do we need that constant? Or we can see that in the third module, while we were discussing about the load flow analysis, we have discussed that active power P variation affects the frequency. Okay, or we can say that angle delta. What is this angle delta? Delta is the load angle or the torque angle of a machine. So active power P mainly depends upon the load angle or the torque angle, which, or otherwise I can say the frequency of a system, or vice versa. Okay, so whenever an active power requirement is there or whenever an active power demand is there, your frequency is the parameter of indication. Whenever you see any change in frequency, its meaning is that whenever there is a change in frequency, it means there is a demand for active power. Okay, or the active power excess. So frequency is actually an indication of active power. Whenever there is variation in frequency, it indicates that something is associated with the active power P. Okay, similarly the reactive power Q affects the voltage or vice versa. That means when there is any voltage rise or fall, it indicates that somewhere there is a reactive power requirement. So this is a basic and the important concept that you need to know. In electrical power system, the frequency and voltage are the indications of active power P and reactive power Q respectively. That means maintaining frequency constant means we are maintaining active power P constant. Similarly, maintaining voltage constant means we are maintaining the reactive power constant. See, these are all discussed by considering the disturbance is very small. Okay, so whenever there is such variation, by using some control mechanism, we will be we will be maintaining the frequency constant, or we will be maintaining the voltage constant. Okay, the control technique associated with that is For maintaining frequency constant, we'll be using frequency control, and for maintaining voltage constant, we'll be adopting voltage control. This frequency control and this voltage control together called automatic generation control. Okay, so an automatic generation control means it controls both the load frequency as well as the excitation voltage. What is excitation voltage? We are dealing with synchronous machine, right? So a synchronous machine will be having a stator and a rotor, and the magnetic field is a rotor. So in order to provide the magnetic field, a DC supply is provided in order to provide this magnetic field. That DC supply, or that is called the excitation given to a machine. Okay, so that excitation, if that excitation is controlled, which can control the voltage of the output voltage, or which indirectly controls the reactive power. So this is the concept. Okay, so whatever it may be, here the main concept is that we need load frequency control for controlling active power, we need excitation voltage control for controlling the reactive power. This frequency control and the voltage control together constitutes our automatic generation control. Okay, so this is what we have just explained, how this P and Q control. Here it will be much more clear. The active power P depends upon the frequency of the machine. Okay. Then how does this frequency depend on, or the frequency depends upon which parameter? The frequency depends upon the turbine speed. We know that in practical case there will be a steam turbine or a hydroelectric turbine whose turbine will be connected to a generator. Okay, and depending upon the speed of the generator, you'll be getting a particular frequency, or you can say that frequency depends upon the speed of rotation of rotor, and the speed of rotation of the rotor depends upon the turbine speed, and the turbine speed depends upon the steam input. Okay, so ultimately you can say that active power P can be controlled by controlling the frequency. And how frequency can be controlled? Frequency can be controlled by controlling the speed of the turbine. How the speed of the turbine can be controlled? Speed of the turbine can be controlled by controlling the steam input. Or indirectly, active power P can be controlled by controlling the steam input. This type of control is called load frequency control, because here we are controlling the frequency for controlling the active power. Clear? Similarly, reactive power Q depends upon the voltage, output voltage, and this output voltage depends upon the excitation of our magnetic field. Okay, so a reactive power Q can be controlled by controlling the excitation of the alternator or the excitation of the machine. This control is called voltage control. Now, how I hope it is clear for you how we can control the active power P and how we can control the reactive power Q. Active power P can be controlled by using load frequency control, and reactive power Q can be controlled using voltage control. Okay. Now, we are mentioning that we need to keep active power constant, or that means we are maintaining the frequency constant. And why do we need a constant frequency? See, this can be asked as a short answer question. Why do we require a constant frequency, or why frequency to be maintained constant? Okay, so this is very simple because we all know this. Because whenever we are what is our frequency? Our frequency is 50 hertz. Now, if ever there is a change in frequency, so our consumers, that means we are most of our equipments, everything is designed for a particular frequency of 50 hertz. So if ever there is frequency change other than 50 hertz, it will affect our plant equipments and ultimately the production process. Okay, similarly, we know that for parallel operation, frequency to be maintained constant. So if different power stations are to be run satisfactorily in parallel operation, frequency should be maintained constant. Okay, similarly, various motors, everything are designed for particular frequency of 50 hertz. So in order to ensure the proper working of all the motors, our supply frequency should be constant. Okay, in most of the plants there will be some clocks which will be configured for our supply frequency. So for everything to function properly, most of the equipments and every clocks, every timing systems, everything are designed for a frequency of 50 hertz. So it is necessary to maintain our frequency as constant as 50 hertz. Okay, so for that we'll be using frequency control methods. Now the idea will be much more clear to you. This is the schematic of LFC, means load frequency control, and VC means voltage control. We are considering a turbo generator. A turbo generator, otherwise called an alternator. Okay, so an alternator, what do we have? This is our exciter. Okay, this is our excitation part, or it itself is a rotor. Rotating part is a excitation, because here magnetic field is being rotated, right? So this is our rotor of our machine. Okay, rotor means which has a magnetic field, that is a term coils over here, and this rotor will be connected to what? Turbine. That means when turbine rotates, this rotor rotates. Okay, and from the stator part you will be connecting, this will be the output. Okay, and this output will be having, that means P plus JQ, that is active power as well as a reactive power. So your output voltage is there, right? And this output voltage is, let it be represented by V, and the frequency of that particular voltage, let it be F. Okay, so from the output you can sense the voltage and you can sense the frequency. Okay, so once a frequency is sensed, if it is what it is being done, it is compared with the, this is reference frequency, F reference. For our case it is 50 hertz, right? So let our frequency here, it is 40 hertz. So it is being compared with our reference frequency, which is 50 hertz. And what would be this block? You know, you have studied in control systems, like actual value is compared with the reference value. Okay, so this is actually a frequency sensor and a comparator, which compares the actual frequency 40 hertz with our reference frequency 50 hertz, and an error signal is generated over here. Okay, so depend, what is a change now? There is a change in frequency of 10 hertz. That means we have to increase the frequency. So for increasing the frequency, you'll be having a steam valve controller over here. Now how we can increase the frequency? Frequency can be increased if the speed of rotation of the turbine is increased. How the speed of rotation of the turbine can be increased? If we provide more steam to this turbine, the speed of the turbine will increase. Okay, so that means this valve is to be opened so that more steam will enter. Now this valve is to be opened, and that control is being done by this steam valve controller. So depending upon the required frequency, okay, the steam valve controller will open the valve or close the valve, thereby increases or reduces the steam input, thereby increases or reduces the speed of the turbine, thereby increases or decreases the frequency of generation. Clear? And this entire part, or this entire thing, comes under what? Load frequency control. And why are we controlling the frequency? Frequency is being controlled in order to maintain the active power constant. Okay, so, or rather by doing so we are controlling the active power. Am I clear? Okay, now let's move on to the next part. The next part here, it is, we have sensed the voltage. Now we have sensed the frequency over here. Now it's time for us to sense the voltage, magnitude of the voltage. So here there is one arrow, it is missed over here. Okay, so voltage is sensed here, and it is compared with the reference voltage. Say our reference voltage is 440 volt. Okay, so here sensed voltage is 400 volt. That means what? We need to increase the voltage. So what block would be this? This is a voltage sensor and a comparator. It will compare the actual value of the voltage with the reference value, and the error will be provided here. And what is this? This is an excitation controller which will control the excitation. So in this case, here actual value is 400 volt, whereas our reference value was 440 volt. So our excitation controller would increase the excitation. Once the excitation is increased, your output voltage will also increase. And this section is called the excitation control, or the excitation voltage control. Okay, so this is the concept behind the load frequency control and the voltage control. Okay, now in the coming section we will see how the frequency control method is adopted, or rather we can say that frequency control is same as speed control of the turbine. Okay, turbine speed control means it is indirectly controlling the frequency. I hope it is clear. Let's move on to the core area of our module, that is load frequency control. Very, very, very important. Load frequency control. In the load frequency control, before proceeding to the modeling of the load frequency control, let's make it more clear what is this turbine speed governing system. So again I am repeating, speed governing means what? Speed controlling, or indirectly I can say that by speed controlling we are controlling the frequency. So it is same as frequency control. Clear? Let's move on to the figure. Very important figure. Okay. Now this is our this is our steam valve. Okay, so here we are providing steam. This is the valve. By if this is moved upwards, it would be closing. If it is moved downwards, the steam valve is opening. Okay, and this steam is given to the turbine. Turbine is not shown in the picture. Okay, so this much is our system. The rest entire thing provided here is for controlling this single valve. Okay, now we will see what all are here provided here. Now the main parts of this speed governing system are, the first one is a fly ball speed governor. Fly ball speed governor. We will see what fly ball speed governor is. You can see two balls here. See two balls. Okay, and these two balls are connected to a single thread. Okay, so which is connected to a point B. A, B, C, D and E are links. Okay, so different links here. Every joint can move by its own. Okay, so that's it. So A, B, C is a link where central point is B. C, D, E is at another link where D is a central point. That's it. So here the function is like this. If A moves downwards, C moves upwards. If A moves upwards, C moves downwards. Okay, and central point is B. So when B moves downwards, everything will move downwards. Okay. Okay, like a link type mechanism. So when B moves downwards, entire thing moves downwards like that. Okay, when C moves downwards, D also moves downwards. The movement of the E depends upon the movement of the piston. Okay, so that we will discuss that later, but now for the time being we'll be focusing on this flywheel speed governing system. So this is connected like this. So in this case I can give you the example. You all might have watched the movie Bahubali. So in the movie Bahubali, you can you remember they were using one weapon like this, two balls, okay, and they'll be rotating that and they'll be throwing to that enemy. Okay, so you can see that when the speed of rotation increases, what happened to the ball? These two balls will move apart, right? So these two balls will move apart when the speed of rotation increases. Similarly, when the speed of rotation decreases, these two balls will move closer. Clear? So this is actually a speed governor, means this denotes the speed of the turbine. When the turbine speed increases, this two fly balls will move apart. When they move apart, it will apply a tension here, isn't it? It will apply a tension here to this point. Similarly, when the speed of the governor decreases, these two fly balls will move towards. So a tension over here, it is released. So that is the mechanism, fly ball speed governing system. Okay. Now the second part, and we will discuss the working later. Now we just familiarize with the different parts. The second one is hydraulic amplifier. We will see what is hydraulic amplifier. See, this is a hydraulic amplifier. This is a speed control mechanism. Okay, so here it consists of a main piston. Okay, this piston is actually for opening or closing the steam valve. Okay, and there is a pilot valve. Okay, here you have a pilot. This is one valve. This is yet another valve. Okay, here some high pressure oil is falling into this area. Okay, and under this position these two valves are closed. See, this is one piston. Okay, piston has two, this is a piston. Okay, so we currently in this position these two valves are closed, so the high pressure oil is there within this. Okay, so a light movement of this piston will causes a heavy movement of the main piston. So that is actually the hydraulic pump, like the working of an hydraulic pump or hydraulic lift. Okay, similarly, by providing a small motion to this small pilot valve or the small piston, it will create a high force or more force onto the main piston, which will open or close the steam valve. Clear? So that is hydraulic amplifier or speed control mechanism. Okay, now the third part is linkage mechanism, that we have already explained the links: A B C link and C D E link. Okay, when A moves upwards, C moves downwards. When A moves downwards, C moves upward. When B is moving down, it's a central point. When B moves downwards, the entire team comes downward. Here it is fixed. Okay, here it is fixed, so we cannot say that motion. When C comes downward, D also moves downward. When C goes upward, D also moves upward. Okay, so that is the linkage. Here we have marked it as L1, L2, L3, L4 for the links, so that we require for the modeling part. Now for the time being you ignore that. Now another thing is the speed changer. Now we will see what is speed changer. So here we have mentioned about speed governor. That means this is the indication of the turbine speed. Now here this is a speed changer. That means if we manually want to reduce the speed, if you manually want to lower the speed, this is just like a weight, like a weight given. You might have done the lab machines lab experiment. How will you load? By providing the load to the machine, there is one weight over there, isn't it? So similarly like that, this is some weight actually, and if it is moved upward, it is actually for reducing the speed. If you want to reduce the speed of the machine, you can move this upward. If you want to increase the speed of the machine, you can move this downwards. Okay, so that is a speed changer which we can do it automatically. So these are the parts of this particular turbine speed governing system. See, so the small description of all that we have discussed is given here. So in the text it is given the different parts. Now let's assume a working. Okay, now let's assume the working. See, if I want to increase the speed of the machine, I'll move this weight downwards. Okay, when the weight is increased, that means when it is moved downwards, the weight over the point A is increasing. So what will happen to this point A? The point A will move downwards. Okay, when the point A moves downwards, what will happen to point C? The point C will move upwards. When the point C move upwards, what will happen to D? D is also moving upward. Now you explain here. When the D is moved upward, this point is now somewhat around this, isn't it? Okay, now what happened? This valve is opened, so your high pressure oil within this will be moving to this valve, and it will be pulling down your piston downwards. Okay, when this piston is moved downwards, what will happen to this valve? The valve here, it is moving downwards. It is moving downwards means your valve is open, and what happens? The entire more steam will be moving to the turbine. What will happen when more steam moves to the turbine? The speed of the turbine increases. Am I clear? I am repeating. If this is moved downwards due to the weight, point A will be moving downwards, or we can say the point C will be moving upwards. When C moves upward, D also moves upward. When D moves upward, the piston moves upward, so this valve is open. The high pressure oil will be moving through the valve, and it will be pushing down the piston, and which will causes the valve to open, and the steam will be flowing to the turbine, which increases the speed. Am I clear? Okay, now we will see the other case. Okay, that is, if I want to reduce the speed, what will I do? I will move the weight over this area. So when the weight over this area is decreased, what will happen? This area will be, this point A will be moving upward comparatively. When this moves upward, what will happen to C? Your C point will be moving downwards. When the C point moves downwards, your D also moves downwards, which will cause what do you call, this piston point to move here, and this piston will be moving somewhat downwards. So what happens here? This valve is closed whereas this valve is open. So your high pressure oil will be flowing through this path and it will be pushing up the piston. And when this piston is pushed up, what will happen? The valve is moved, or I can say that when this piston is moved upward, what happens? No steam or less steam will be flowing to the turbine. Clear? So that thereby it will reduces the speed. So this is how we can control the steam input to the turbine. Okay, this is one way. Now, and this is by manually by adjusting with the help of speed changer. Now we will see how automatically it is happening. So when the speed, if a particular speed is set for this machine, and if the speed of the machine, excuse me, one second. If the speed of the machine increases, what happens? This fly ball will move apart. When this fly ball will move apart, it will create a tension over here. So it will create a tension over here and this point will move downwards. Okay. So when this moves downwards, what happens? Your C moves downwards. Rest you know. And D moves downwards. So what happens? The same thing happens. Piston and it will move upwards, which thereby it reduces the steam input and finally it reduces the speed of the turbine. Okay, now similarly we can consider the next case. Next case means if the speed is less. Speed is less means the fly ball will come to each other. So what will happen? Your point B will move upwards. Okay, and what happens to your C? C moves upwards. And what happens to D? D moves upwards. So when D moves upward, what happens? Like this, isn't it? It will push the piston down. That means it will cause downward movement and the steam will be flowing and it will be what do you call, increasing the speed of the turbine. So this is the mechanism behind the speed governing system. So this can be asked as a short answer or as an essay for turbine speed governing system. So this is a concept behind this. So for the entire thing, we are controlling the speed of the turbine. If the speed of the turbine is controlled, what is actually controlling? We are controlling the frequency of the output. So that is why this is called load frequency control, which is controlled with the help of a speed governing system. So frequency is controlled means this is given to a turbine. So this entire thing is just the control of the turbine. Then you will be having a turbine and the output of the turbine will be connected to a generator, and the output of the generator you will be having the load. That frequency is being controlled with the help of this entire control mechanism. So once again, which are the different parts of this speed governing system? One part is fly ball speed governor. The second part is what do you call, the hydraulic amplifier. Okay, and the third part is the linkage mechanism, and the fourth part is speed changers. So if you can thoroughly understand the concept, it is very easy for you to write in detail, whether it is for 10 marks, whether it is for 5 marks or 7 marks, depending upon the marks you write accordingly. Okay, and so in today's lecture we have discussed the need for automatic generation control, how the active power P and the reactive power Q affects the frequency and the voltage, or vice versa. That means how the voltage and frequency is being affected by the active power and the reactive power. In both ways we can see the active power mainly depends upon the frequency and the reactive power mainly depends upon the voltage. So for controlling active power we need frequency control, for controlling reactive power we need voltage control. This frequency control and the voltage control is together called automatic generation control. And in this lecture we have discussed about the load frequency control, and that too we are considering single area network, and in that we have discussed the turbine speed governing system. Okay, in the next lecture we will be discussing the modeling of load frequency control. For that, this concept should be very clear to you. I hope this much is clear to you. If you have any doubt, please feel free to contact me, and I'll be sharing the notes as well to your Google Classroom. Okay? Thank you. In this direction. So when in this direction it is closed means